So here's an example here. Here's water. And this is water actually reacting with another water. So in one case, water is an acid. In the other case, water here is a base. So in this particular case, he would send over an H plus. The result of that is we will form OH minus, and we will form our hydronium ion here as well. Now, earlier we saw water acting as a acid in that case. In this particular case here, where we wrote this reaction, our hydrochloric acid is our acid. Our water is acting as our base in this and accepting the H plus. And again, the result of this is we will get H3O plus and Cl minus. Now, the acid here would be related to this guy, which would be the conjugate base. The base here would be related to this guy, which would be the conjugate acid. The only difference between those guys is that one H plus. This guy has one less H plus. This one has one more H plus. Now, again, regular acid and bases on the left-hand side of the arrow, are conjugate guys on the right-hand side of the arrow. And this reaction that I just wrote, in the reaction that we see here and the reaction that we see in the previous one, we have seen that water in some cases acted as an acid, and in other cases it acted as a base. And there are certain species that can act both as an acid or a base, depending on the situation. And things that could act as both an acid and a base are known as being amphoteric. So an amphoteric substance is a substance that can act as an acid or a base. So water is an example of that. It has the ability in certain cases to act as a base, has in certain cases the ability to act as an acid, and that is what basically the definition of amphoteric basically means. Any questions on that there? All right, so let's take a look at some here and see if they are conjugate acid base pairs. So for each of these that you have, which of the following would be conjugate acid base pairs? So take a moment and see if they are related to each other. Okay, let's take a look. So the key to determining if they are related to each other in terms of really the Bronsted-Lowry definition is the H plus. And once again, that should be the only difference between the two things. If it is anything other than just one H plus, it is not going to be a pair. So let's take a look at this one, HCl, and I don't know why books write it that way, but ClO minus, right? All right, so in this case, the difference between this guy and this guy is an H plus, but there's also a difference of a oxygen that this guy has and this one does not. So because of that, they would not be pairs. So that guy would not be pairs again, because there's more than just an H plus difference. H2SO4 and SO4 2 minus, are those guys pairs? The answer is no, they are not pairs, because the difference between this guy and this guy is 2 H pluses, too many. It could only be one H plus, and that's the only difference. So those guys are actually, they are related to each other, but they are not related to each other in terms of it being a acid conjugate base pair. How about ammonium and ammonia? They are, again, the only difference here is one H plus, so that is a winner so far. Again, you could either take the H plus off of this guy and you should end up there, or put the H plus on this guy and you should end up there, whichever way you want to kind of look at it. We got H3O plus and OH minus. Are those pairs? Those are not pairs. Again, the difference here is actually a couple of H pluses as well. So they are not pairs. And obviously none of the above would be incorrect since 3 looks like a winner in this case. Question on that there. Now, to answer maybe the question you may have, but you didn't ask, which is about this guy. So that guy there does come from H2SO4, which is a diprotic acid, and a diprotic acid means it's got 2 hydrogens it can give off. Now, you may be deceived by what you learned maybe in the previous class or a previous class. We oftentimes look at the overall reaction when we think about sulfuric acid, for example, breaking apart. But hydrogens actually do come off actually in a stepwise fashion. They come off basically one at a time. So in this situation, what would happen is the H2SO4 would dump off 1 hydrogen and make HSO4 minus. The next step that would take place is actually the HSO4 minus would dump off another hydrogen to make SO4 2 minus in this case. So what you might be familiar with or looked at or seen before is if we add these together, that guy and that guy cancels, and it gives us that H2SO4 gives us 2 H pluses and SO4 2 minuses. And that is the overall reaction that is taking place, but it does happen in a stepwise fashion. That is why when we look at something like this guy and this guy, are they partners? They are partners. The only difference between them is 1 H plus. So if you put the H back on the guy on the right, you get 2 H's. Plus 1 and minus 1 gives you 0, which gives you the guy on the left. So those guys are partners. HSO4 minus and SO4 2 minus, are they partners? They actually are partners as well. The only difference between those two is 1 H plus. Again, if you take off the H from the guy on the left, you're left with SO4 minus. And when you take off the H, is actually a plus. So you become 1 more negative, and it becomes SO4 2 minus. So those guys in green on either side there, these two guys would be partners. These two guys would be partners. But if we jump like we did in this question from here to here, that's basically a 2-step process there, and it would not make them partners in that case. Question on that there. Okay. So let's try this. We're looking for the conjugate acid for the guy right here. Right answer should be up there, hopefully. Let's see. Where's the conjugate acid for that guy right there? So let's take a look. If we have this guy here, we know that we want to put on either an H plus or take off. So either add an H plus or remove an H plus in this case. So in this case, we are looking for the conjugate acid to this base. And the important thing to think about is the relationship that we talked about, which is an acid and a base. On the left-hand side, the conjugate acid, right, and the conjugate base. Now, in this case, it did ask us for the conjugate acid. And what we know in terms of partners is this is the relationship, right? Those are 2 things that are related to each other. So if we are looking for the conjugate acid, that means what we are looking at is a base, and the Bronsted-Lowry definition of a base is it should accept, right, an H plus, which means that is what we would want to put on there. So we would add on an H plus here, and that would get us, I think I left off a couple of things there. I left off the H, which would be good there. There we go. That looks better. So we would add an H onto there and a plus, and that would give us C6H5 NH3 plus, which, as you correctly said, would be number 2 there. Yeah. So sometimes it's helpful in a lot of problems. They will not tell you, hey, this is an acid, this is a base. they will just simply ask you to write the formula for the conjugate acid or conjugate base. So if you think about it backwards of where it came from, and just use the Bronsted-Lowry definition of either an acid will donate off the H plus or a base will accept it, you'll be able to do that. All right, so take a moment here for this particular one and write the conjugate acid for this guy, and also write the conjugate base. So take a moment there and write both of those, starting with this guy. Okay, let's take a look. So once again, in this situation, the decision is add the H plus or remove the H plus. So we'll start with the guy on the right here. We're going to look for the conjugate base starting with this. So once again, if you're not sure what you're dealing with, you do know that you want to end up with the conjugate base, which if we follow the pathway back here, that means what you are looking at that point is an acid. And an acid would mean, based on Bronsted-Lowry definition, you should donate the H plus. So that means we should remove the H plus. So in this case, when we get rid of the H, we're left with a CO3. And once again, it's not just the H, but the plus is important here. So when we remove a plus, we become one more negative, and we will end up with carbonate, basically here would be the conjugate base. Any questions on that one there? Now, if we're going to do the guy on the left there and starting with the same guy, we're looking for the conjugate acid. So much like the previous example, we are looking for the conjugate acid, which means if we follow the backwards thought process here, that we are looking at in this case is it is going to act as a base in this case. Definition of a base is somebody that will accept the H plus. So in this case, we're going to put the H plus onto this. When we put the H on, we end up with an H and a 2, a CO3, plus 1 and minus 1 equals 0. So we end up with basically carbonic acid here, H2CO3. Question on that there. So again, a lot of questions, they won't tell you it's an acid or base. You got to kind of think about it backwards to determine it. And you can just use the basic definition of the Bronsted-Lowry definition of an acid and base. This is also another guy here that can act as an acid or base. That is an amphoteric substance, just like water. You will come across a lot of these guys that have an H and a negative charge. Those are guys that really can, in a lot of cases, act either as an acid or base because it has the H to donate, and it also can accept the H plus because it has a charge as well, and it has kind of room to accept the H plus. So a lot of those guys have an H and a negative charge. You know, they could kind of go both ways. And we'll talk about later on in this chapter how you determine sort of which way will it do it. Will it act as an acid? Will it act as a base? You could kind of make that decision actually a little bit later on as well. Any questions on Bronsted-Lowry conjugate acid base pairs? Okay. Then as we talked about, water can react with itself, and it actually does set up an equilibrium. It is what's going on in all solutions that involve water. And because it could set up an equilibrium, well, we could write an equilibrium constant for it. But just like normal, we would not include, right, the water as it is a pure liquid in it. So really the equilibrium constant for this would be what is referred to as Kw, which would be the concentration of H plus times the concentration of OH minus. It actually has a value at 25 degrees of 1 times 10 to the minus 14. This is one of those formulas where you could also write H3O plus times OH minus equals 1 times 10 to the minus 14. So again, you can use H plus or H3O plus, whichever way you like. Once again, I'm going to personally use probably H plus. So the concentration bracket is molarity in this case. And we could use Kw, which is the ion product of water, to help us understand whether or not a solution will be acidic, basic, or neutral. So in this case, once again, it is 1 times 10 to the minus 14. We could rearrange this and solve for H plus. It would equal 1 times 10 to the minus 14 divided by the concentration of OH minus. Or if you have the OH minus concentration, it would be 1 times 10 to the minus 14 divided by the H plus concentration. Good news is it's basically the same calculation. You basically put 1 times 10 to the minus 14 divided by whatever one they give you, and it will give you the other part. You could think of the H plus part of this as the acid part, right, of the solution. The OH minus is the base part of the solution. The concentrations of each of those things run opposite of each other. So as the concentration of H plus increases, the concentration of OH minus decreases. So they do run opposites of each other. And obviously vice versa, as H plus goes down, OH minus concentration will go up. So you could actually calculate some numbers here for the H plus and the OH minus. And if the H plus equals the OH minus solution, that means actually they both will equal 1 times 10 to the minus 7 molar. It is going to be a neutral solution. So the solution will be neutral. If the acid concentration, the H plus concentration, is larger than the OH minus concentration, it will be an acidic solution. And if the OH minus concentration is larger than the H plus concentration, it will be a basic solution. So you could actually calculate both the H plus concentration and the OH minus concentration in the solution. You could compare the two values, and whichever one is larger, it will be either acidic or basic, depending. And if they're equal to each other, it will be neutral. It is extremely important in this chapter and all other chapters, but really in this chapter as well, that you make sure you are using your exponent button and all these calculations on your calculator. Otherwise, you will find yourself off by a factor. Yeah. So you seem, as we go through some of these things, and you're like, my number looks really good on the front part, but the times 10 to the whatever part is just off. It is probably the way you're punching into your calculator. So definitely make sure you use that EE button, that EXP button when you're doing these problems. All right, so let's try one here. What is the concentration of hydroxide in an HCl solution that has a hydrogen concentration of 1.3 molar? Okay, let's take a look. So here we would use Kw, which is our H plus concentration times our OH minus concentration, and equals 1 times 10 to minus 14. In this case, we are given the H plus concentration of 1.3. We are looking for the OH minus concentration here. So rearranging and solving for the OH minus, that would equal Kw divided by the H plus. And that would be 1 times 10 to the minus 14 divided by 1.3 in this case. And that's going to give us 1 to the minus 14 divided by 1.3. Going to give us a 7.7 times 10 to the minus 15. This would be molarity, as it is a concentration unit, so we do need these units in there. In this case, is it acidic, basic, or neutral? It is acidic because the H plus concentration at 1.3 is greater than the OH minus concentration. So it would be acidic, which we would hope, because this is hydrochloric acid, right? So we would hope that guy would be acidic. If it's not, then definitely something probably went wrong somewhere there in the calculation. Any question on that one there? All right, let's try another one, I think. In a solution where the H plus concentration is 1.2 times 10 to the minus 6, what is the OH minus concentration in the same solution? And is it acidic? Equals 1 times 10 to the minus 14. And by the way, if the temperature wasn't 25 degrees Celsius, would this number change? It would, because it's an equilibrium constant value. So in most problems, probably 99.9% of the problems, you can safely assume, even if it doesn't tell you, that it is 25 degrees, and you can use that number. If they do tell you by some chance that it is a different temperature, they probably either refer you to a table or give you a different value for kW to use, but pretty much is a safe bet to use that. But just be aware, it is still an equilibrium constant, and it does change the value with temperature as it changes. So in this case, we are given the H plus. So once again, here we're going to look at the OH minus, which would be kW divided by H plus. And that would give us 1 times 10 to the minus 14 divided by 1.2 times 10 to the minus 6. Making sure we use our exponent buttons when we punch that in there, it gets us an 8.3 times 10 to the minus 9 molar. Or if you have a lot of calculators, a bunch of zeros and an 8 at the end as your calculator right out of the room, basically, if you're not in scientific notation. First off, any question on the calculation there? Is this acidic, basic, or neutral, this guy? So we are comparing, again, the H plus concentration to the OH minus concentration. And in this case, the H plus concentration is larger, and it would be acidic. And just in case, right, the negative part of this number, right, is important because the -6 means you're going 6 places to the left and adding zeros, but the -9 means you're going 9 places to the left, right, and adding zeros. So when you have a negative exponent, right, the larger number is actually the smaller number, right, when you turn it into like a decimal type number. Any questions on that there? Okay. So the next thing we're talking about is the pH of a solution. And a way that we measure if a solution is acidic or basic is to use the pH scale and to calculate the pH. And the pH scale does run from 0 to 7 to 14. Below 7 is acidic. Above 7 there is basic. And really, truthfully, dead on 7 is neutral. And as you go from 7 towards 0, you're becoming more acidic as you go this way. And as you go from 7 up to 14, you're becoming more basic as you go in that direction. The way that we calculate the pH is we take minus our negative of the log of the H plus concentration. Once again, this is another formula that you can substitute H3O plus in there if you would like to. It's the same thing. Depending on your calculator, you need to punch this formula in a specific way, and all the other ones a specific way. If you have a display calculator, you should punch it into your calculator the exact same way the formula is written. Negative log and then the H plus concentration, probably using your exponent button. If you have a non-display calculator, this one and all the other ones, you actually need to start with the number, then hit log, and then hit the negative. So you have to work backwards. If you're not sure what type of calculator you have, hit the log button. If it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator if it says error. Yeah. So again, if you have a display calculator exactly the way it's written, non-display, this one and everybody else, you got to head in the opposite direction. Again, here, if we calculate the pH, that's usually what we want to use to figure out if it's acidic, basic, or neutral. Why a pH of 7 is neutral is because exactly those concentrations are equal to each other. And if you put that into the pH equation, that is what you get for 7. So that there is no misunderstanding for us in here, we're going to roll with exactly 7 is neutral. If it's a little bit above 7, it's going to be slightly basic. If it's a little below 7, it's going to be slightly acidic. So there's no misunderstanding. 7 on the nose there for neutral. If it's acidic, it obviously will have a pH that is less than 7. And if it's basic, it will have a pH greater than 7. As you go that way. Now, speaking of using our calculators to calculate this, let's try one here. Actually, let's talk first off about sig figs and pH type of calculation. The number of decimal places in your pH type of calculation should equal the number of significant figures in your concentration value. So the number of decimal places that you should put out there for your pH or pH type of value should be the same number of decimal places as the number of significant figures your concentration has. So why don't we calculate one? What is the pH of a solution that has an H plus concentration of 2.5 times 10 to the minus 6? All right, so calculate that up, see what you get. I will as well, since I just made it up. Hopefully we'll end up in the same spot there. All right, so when we put this in, whichever way you're going, either negative log 2.5 exponent button, negative button, and 6, or going the backwards way, 2.5 exponent button, negative 6, log, and then the negative button. You should get on your calculator this number, 5.6020599991. So first off, hopefully you got a number that looks something like that. How should we report this? Should we report this as 5.6? Should we report this as 5.60? Should we report it as 5.6020599991? Which one would be the correct way to report this one? I heard 5.6 and 5.60. Thankfully, I did not hear anybody say this number here. Too many. All right, so what the rule is in this case, we will look at the concentration number. And this number here has how many significant figures? It does have 2 significant figures, which are those 2 right there before the times 10 part, right? So anything before the times 10 part is significant. The number of significant figures in our concentration value is not how many significant figures our pH should have, but it is how many decimal places we should have, which would be 2 decimal places. So the correct answer should be 5.60 in this case. So 2 significant figures in the concentration translates into 2 decimal places, not significant figures, but 2 decimal places in the pH value. We're going to talk about obviously going backwards as well, going from pH to the concentration. You would follow the same rule if you had 2 decimal places in your pH value. When you would calculate your concentration, you should end up with 2 significant figures. So it goes both ways as you're calculating it. By the way, to finish up on acidic, basic, or neutral, this one. It is acidic. It is less than 7 there. So it would be acidic. All right, any questions on that? Talked about the pH, obviously, equation. There is a similar sort of scale, but it measures OH minus concentration, and that's what's referred to as the POH. And the POH is equal to minus the log of the OH minus concentration. Again, not to be confused with the pH, which is minus the log of the H plus concentration. The name actually tells you what you need. pH, you need the H plus. POH, you need the OH minus concentration. Why that's kind of nice is there's a nice relationship between pH and POH. If you take the pH plus the POH, it will equal 14. So if you have just the hydroxide concentration, you could calculate the pH, POH of that solution, and then simply subtract 14 from it, and you would have the pH pretty easily. If we add in a couple other sort of calculations that we will sometimes see, if you do have the pH, you could get the H plus concentration from that. And the H plus concentration would equal the inverse log of the minus pH. Now, most people's calculators, when they hit the inverse log, that's like the 10 and the caret is usually what pops up. And then you want to make sure it's negative pH in this case. Usually to get the inverse log on most people's calculators, That is the upper left corner. There's usually a button like shift or second button up there. And then usually above the log button, you'll see this 10 to the X, which might be how you've been doing scientific notation incorrectly, but that's actually what you use it for, is the inverse log is actually that button there. You could also, if you have the POH, you could get the OH minus concentration from it. It's the exact same calculation. It is the inverse log of the minus POH. And once again, that most likely will look like a 10 and a caret POH on there. If we add in our other one that we talked about just a second ago, which is our KW, equals H plus times our OH minus concentration equals 1 times 10 to the minus 14. This does give you a variety of different ways at which you can actually solve a problem. So there is kind of more than one right path depending on sort of what you choose. As long as you choose sort of a correct formula and equation and pathway, everybody should get to the same place, maybe a slightly different with a little bit of rounding, but should pretty much end up the same how you do it. So in some cases, you may not even have to use KW. You could just kind of use the inverse log. But if you want to still use KW, you can as well. So there's a variety of ways you do it. On the left-hand side here is the pH scale. And again, we see some things. We got some HCl, some acids down here, which obviously are acidic. Up here, like we talked about, is kind of cleaners, and sodium hydroxide is basic. We have pure water here, which is about 7. If I take water that's maybe not pure water or water that's been sitting out, say out on the countertop in your beaker, will the pH be 7? It will not. It actually will be like acidic. It'll be like in this range probably. And that's because it picks up some carbon dioxide from the air, makes some carbonic acid, increases the H plus concentration in the solution, and lowers the pH a little bit and stuff like that. So sometimes people are surprised when they take this guy here, which is a pH meter, and they're surprised that when they stick it in there, my water is like kind of acidic there when they do it. So a pH meter measures the pH of the solution. It really measures the H plus concentration that's floating around in that beaker. In reality, what it really measures is kind of the voltage that you tell it, like this is a pH 7, this is a pH of 10, this is a pH of 4. And then it does sort of a calibration curve and figures out by the voltage of what it sticks into your solution, what the pH would be after you calibrate it. That's obviously a very good way to do it. We'll start using those pretty soon in the next couple of experiments. But it's a good way to just gives you the pH straight up what it is. Other ways we could get the pH is we could use something like pH paper. pH paper, you dip your solution onto the paper, changes color, you kind of move it around to match up the color on the paper to the chart. If you maybe have a pool, ever did any pool care, they're kind of like those little test strips you put in the pool and it all changes color and you kind of check everything. We also use litmus paper sometimes. It doesn't give us an actual value for pH or anything like that, but we do use litmus paper to tell us if it's acidic or basic. And a reminder that if litmus paper turns red, it's acidic. And if litmus paper turns blue, it is basic. So again, it doesn't give you obviously a pH value for it, but it will give you an idea as to whether or not your solution is acidic or basic. All right, any questions on any of those there? All right, let's try some here. The pH of rainwater collected is about 4.82. Let's answer a bunch of questions here. Let's do, like it asks, what is the concentration of H plus? What is the concentration of OH minus? What is the POH? And is it acidic, basic, or neutral? For the second one, we have the OH minus concentration is 2.5 times 10 to the minus 7. Let's do what is the pH, the POH, the H plus concentration. And again, is it acidic, basic, or neutral? All right, so take a couple moments there for each of those and see what you come up with. Make sure you understand how to properly punch them into your calculator. All right, let's take a look here and see how we're doing. So in this case, we do have the pH given to us on the first one. So we have a pH here of 4.82. This does give me a couple of options. I could do the inverse log to get the H plus. I could also get the POH really easily. So I'm going to start with the POH. So the POH in this case would equal 14 minus our pH. So that's going to give us 14 minus 4.82. And that is going to be 918. Now, again, I'm going to use either the pH at this point to get the H plus concentration, or I can use at this point the POH to get the OH minus concentration. So I'm going to take this and go that the H plus concentration equals the inverse log of the negative pH. Again, when you put that into your calculator, most likely a 10 and a caret will pop up. You want to make sure you do the negative 4.82. And if we do that on my calculator here, hit the right button, negative 4.82. We're going to end up here with, we'll call it 1.5 times 10 to negative 5, if I counted those zeros right. We do need a molarity there as it is a concentration, so it should have units. Any questions on that there? Now, at this point, you really still have two options. You could use kW and take 1 times 10 to the minus 14 and divide it by that number. Or you could do the same sort of calculation you did with the POH here. And you could do that the OH minus concentration would be the inverse log of the minus POH. That again is going to give you kind of like a 10 and a caret minus 9.18. And that would get us, looks like a 6.6 times 10 to the minus 10. Once again, we do need a concentration unit there, which would be molarity. This would be acidic, basic, or neutral. This would be acidic. You want to look at the pH here. So it is going to be acidic. Again, a couple reminders. There is only one answer to that question. So it shouldn't be acidic and basic at the same time, the same solution. I've never had anybody kind of go all three, go acidic, basic, and neutral at the same time. But what usually will happen sometimes is people will look at the pH and go, it's less than 7, it's acidic. Then people will look at the POH and go, hey, it's above 7, this is basic. They actually do run opposites of each other, the pH and the POH scale. If you have a high pH, you have a low POH. And if you have a low pH, you have a high POH. So they are actually opposites of each other. Most people have the pH scale in their head, so that definitely is the one you should look at in most cases. And again, never give all 3 answers or 2 answers, just one. Any questions on any of that there? Other thing that we also talked about last time in terms of that sig fig sort of situation, our pH there had 2 decimal places. So our concentrations really ended up with 2 significant figures. So again, going back and forth on those, you do want to kind of follow those same rules. Any questions on any of those? Yeah. What's that? It is acidic because you would look at the pH here. That's 4.82, and that is less than 7. You could also, in this case, look at the H plus and OH minus concentration like we did previously. Should give you the same answer if you want to look at that. But really, the pH is probably the easiest one to look at. Other questions? All right, let's take a look then at the second one there. And in this case, we actually have the OH minus concentration, which is 2.5 times 10 to the minus 7. So really, I'm just going to go right into the POH because I can do that. That's minus the log of 2.5 times 10 to the minus 7. Remember, we want to make sure we use our exponent button properly here. So I'm going to do a little log 2.5 minus 7. Looks like we will end up with a 6.60 as our POH. Now I could very easily get the pH because it should be 14 minus the POH. And that would give me 14 minus 6.6. And that would then get me like a 740. And really at this point, we have a couple of things we could do. We could use the pH that we just got to get the H plus concentration. Or again, you could just roll like we did earlier and use KW here. And we could use that relationship if we wanted to. And again, they both should get you really the same answer. So in this case, if we did the H plus, it would be 1 times 10. Oops, not the sin. There we go. -7. Looks like 4.0 times 10 to the -8 molar in this case. And in this case, it would be slightly acidic at this point with the 7.4. There we go. Again, following the same rules that we were talking about in terms of, again, sig figs, we had 2 significant figures there. That meant 2 decimal places really on these numbers. And then obviously we would just say list 2 on that guy as well. Any questions on any of those there?